Um, Next tutorial is given by Professor Giacomo INDIVERI. So he's a professor at the University of Zurich and ETH Zurich. He's working kind of at the intersection of neuroscience, computer science, and machine learning. He works on neuromorphic circuits to both validate brain-inspired computer paradigms in real-world scenarios, as well as developing new generation of fault-tolerant and event-based neuromorphic computer technologies. And today he will give us an introduction on bio-inspired neuromorphic circuits and architectures.
Thank you, Peter. Thank you for the introduction. It will be a pleasure to tell you about bio-inspired neuromorphic circuits and architectures, and somehow relate the word neuromorphic intelligence to artificial intelligence. I know I'm preaching to the choir here when I talk about artificial intelligence, and so this is just a quick summary to remind you that artificial intelligence has been around for many, many years, actually from the late 1940s, but only recently it became very popular. And thanks to the advent of the new technologies, the new algorithms, and the new data sets, we started to really outperform conventional approaches, brute force engineering, and even humans doing superhuman performance. And mainly thanks also to the backpropagation algorithm. And one of the most sort of striking types of networks that we've also seen in the previous tutorial are these convolutional neural networks that are mainly being applied to vision. But as we saw for the auditory scene analysis, they can be applied to images created, for example, from auditory sensors by looking at the spectrotemporal pictures or frames. And this has been extremely successful. And in fact, since the advent of this new generation of convolutional neural networks, many different groups started to create different types of networks. And here on this plot that was taken from a paper of Bianco et al., you see the different types of networks that have been proposed throughout the years from 2000 up to 2018, actually. And we can see that they improve in accuracy by increasing speed. So the way to sort of the brute force approach that has been done so far was really to make networks faster. And also, if you look at the size of these circles, that's the size of the network in terms of memory requirements. And so these networks can have higher accuracy also because they are larger. And this has been sort of a trend, the quick and dirty trick to get networks, AI networks, CNNs, or deep networks to have higher performance is really to increase their size and make them faster. In fact, if you look at the latest, GPT-3 is a network that has a huge size. It has 165 billion parameters, which requires more than 350 gigabytes of memory. It's not something that we worry about in tinyML, but it's just to give you sort of some raw numbers. And if you think what it takes to train these networks of this size in terms of time, which then is and energy, which then is translated into money, it's over $12 million US. So this is clearly a problem. And also in the context of tinyML, even for smaller networks, memory and energy is a clear problem that we as a community are trying to address. And this energy intensive issue is something that we really would like to solve. There are many approaches, as we've seen also this earlier tutorial, but it's really one of the most crucial points. And in fact, the strength or the growth of this community is really recognizing that this is a problem and providing solutions. So it's really nice that there is this community providing these solutions. One of the main reasons for high energy is really data movement. If you think about it, the energy for the computation is actually very, very small. It's negligible to the energy required to transfer data from the memory to the CPU in classical von Neumann architectures. Or if you have multi-chip systems from DRAM to cache, and from external peripheral RAM to DRAM and so on. So that's really the most expensive operation in terms of energy consumption. But this is not the only problem that AI is starting to face. There is also the problem of theoretical and algorithmic approaches. So this idea that narrow AI is not sufficient to sort of reach the levels of intelligence that we see also in animals. As you know, whenever you program a deep network, it's most likely going to be very, very specific to a particular domain. So these deep networks are programmed to perform a limited set of tasks, and they operate with a predetermined and within a predefined range. So there's this need to explore also different types of algorithms and different architectures. In fact, even Geoff Hinton, who was one of the inventors of backpropagation, among others, is sort of critical in this approach of just focusing on one strategy, one path to just, for example, implement backpropagation through time and try to make local incremental changes in these algorithms without worrying about the fact that there might be completely different solutions and architectures that are far away from this sort of local minimum that could lead to intelligent architectures that are as intelligent as the ones found in animal brains. And even Geoff Hinton, I was saying, is deeply suspicious of his own backpropagation algorithm. He doesn't think that this is how the brain works, and he actually thinks that some bright student will overcome the limitations of these algorithms by questioning all of these things. And this is sort of an encouragement I give to all the students there to question everything that is being said, also in this presentation by myself. By the way, these slides will be made available, and whenever you click on the links in blue in square brackets, you get access to the source of the information. So here, this was medium.com paper, and then there are actually scientific publications and so on. So if you want to know more about these things, the information is there. It's just a click away. So now, how do we solve these problems of architectural problems, algorithmic problems, deep theoretical problems? There are several pathways to follow. So this is a slide that was taken from a recent paper of John Schalf, The Future of Computing Beyond Moore's Law. Again, if you click on this link, you can actually access it. And if you see, there are different ways of making progress in improving performance. One is exploring new materials and devices. And this is actually something that is very promising, is being done by looking at different types of materials, resistive memories, spintronics, quantum, photonics. Another approach is to really look at more efficient architectures and packaging. And this is something that we've seen also in the previous tutorial. How can we actually use the standard design flow of synchronous logic, but improve it by changing the architecture, changing the packaging, and looking at different solutions, 3D VLSI, trying to limit the problems of dark silicon, and so on. But also what is nice is that John Schalf points that new models of computation, so this problem of the algorithmic and theoretical paradigm, can actually lead to improving performance. And among the new models of computation that are being proposed by also others that have high potential for solving these problems, and so solving many of the problems that the tinyML community also has, is the one of neuromorphic. So neuromorphic architectures, neuromorphic intelligence, neuromorphic computing. So what is this term neuromorphic? What does that mean? And that's what this sort of tutorial is about. It's really to try to give you a quick overview and sort of also a background. And the term neuromorphic actually comes from different communities. The original term was coined by Carver Mead in the late 80s, early 90s, as I said, when he was pointing out that it's possible to understand how the brain works by trying to reproduce its function through electronics, by using the same physics of the transistors to reproduce the biophysics of the cell. So it was really a basic research approach, fundamental research. There were no applications in mind then. And the idea was really to understand by building. So we can, there's a lot of study and literature on studying the brain from physiology and anatomy, but we can actually try to reproduce the functionality by using the same physics, but by building it. And the nice thing is that transistors in the analog domain, in the weak inversion, actually use diffusion, which give rise to exponentials, which is exactly the same mechanism that ions use to flow from inside and outside the cell, which then give rise to action potentials, spikes, and neural processing in general. So this was a very innovative idea. Together with actually Misha Mahoad was his first student who was a biologist. Carver is an engineer, and together they really created the whole field of neuromorphic engineering. In the maybe around 2010, early 2000s, the neuromorphic computing domain became very popular, mainly pushed by the Synapse DARPA program, by the IBM True North chip, by the Human Brain Project, which was also funding large initiatives such as the Brainscale architectures or platform and the Spinnaker platform. And now more recently, the Intel is also investing a lot in spiking neural network chips. And because they are spiking and they're spiking neural networks, they are being called neuromorphic. They have some analogies to the morphology of the nervous system. And therefore they could potentially solve some of the problems that neural systems are being programmed to solve. The main difference between this more recent approach and the original one is that in this more recent approach, most of these chips, not all, but most, are only digital. There is not no subthreshold analog computation being done. There is this idea of emulating the physics is lost, and mainly it's because these attempts are mainly application driven, and the goal is not to do very fundamental research that might require 10 or 15 or 20 years to lead to something, but really get something to work in the next 3-5 years. And so the digital approach is more reliable, it's easier to control, it's easier to manufacture, and that's why these are some of the reasons why this neuromorphic computing approach came about. And then also in around 2008, the missing element was found. This memristor was proposed. Essentially, it was a device that had been already investigated for many, many years in the field of memory technologies, but it was found that it actually had some properties which were similar or actually reproducing the theoretical work of Leon Chua, and therefore this whole field of memoristic devices, memoristic computing came about. Essentially, these are devices that can store the state of the device in a non-volatile way, by just by applying a pulse and changing the ionic structure of these devices in many of them. And therefore they remember the state. So they are small devices. They are actually quite diverse and inhomogeneous, but they have this non-volatility feature. And therefore they are very similar to biological synapses. And for this analogy between the biology, the neurons and the synapses and the physics of these devices, they were also denoted as neuromorphic. And now the neuromorphic intelligence term, I would like to propose it as something that can bridge across all of these communities and approaches, from the basic research to the applied research to the memory technologies. So the neuromorphic intelligence approach that I will describe in the next few minutes is really deeply rooted in biology. It's really important to understand how the brain works in order to reproduce some of its functions and maybe make some progress and solve some of the problems that conventional approaches are starting to face. One of the main strategies is to employ the physics of silicon and of memoristic devices to emulate neural processing, combine analog and digital in a judicious way, try to take the best of both worlds, and of course, solve applications. We really want to create a new field that can then lead from basic research to applied research to really being deployed in society and be used, for example, to solve some of the problems that the tinyML community is also trying to solve. I'll start from the first point by explaining why is deeply rooted in biology an important point. And I just want to have one single slide highlighting the difference between standard neural networks and biological neural networks. In standard neural networks, the neuron is something that accumulates signals, a weighted sum of inputs, performs a sum and then a nonlinearity, and then sends the output to the next layer, to the next neuron. Most of these operations are independent of time and independent of space. So this is called a point neuron. It doesn't matter if you change the order of your inputs, if you shuffle the A, B, and C. All you have to do is to have a weighted sum, which is a linear operation. Of course, it's a very powerful operator. Already from McCulloch and Pitts, it was shown that it has an isomorphism with Boolean logic. And so you can actually implement Turing-complete structures with these types of units. So from that point of view, it's an extremely efficient model for doing computation. In biology, it's not as simple. The neurons in biology have different morphology. So each neuron actually has a different structure. And then the structure of the neuron determines the functionality. So the way the inputs are collected, the way the output is produced, the length of the axon, all of these features actually change the functionality of the neurons. And so in biological neural networks, there is no concept of point neuron. There is a 3D morphology to it, which determines the functionality. There is time is actually, physical time. In artificial neural networks, time is completely an abstract term. And in biology, time is physical time. It just evolves naturally. And so the time evolution of the physical elements is used to carry out the computation. So the structure of the network is the algorithm. It's really impossible to distinguish the software from the hardware. It's the same thing. The way these neurons are built and the way they are connected, the way the wires are wired together determines the algorithm, and the evolution of time runs the algorithm through the dynamics of the system. So it's really a different way of doing computation than writing a piece of Python code and then mapping it onto some hardware that is completely independent of the Python. So it's something completely different. And if we want to try to solve some of the problems that tinyML wants to solve using this brain-inspired approach, we really have to try to take a step back and try to think of completely different architectures. And there are two main points I would like you to remember if you want to follow this path. The first one is related to space and memory. As you know, von Neumann architectures are mainly characterized by having different memory blocks that are, either a bit far away or really far away from the central processing unit, from the processing blocks. And this is leading to the infamous von Neumann bottleneck, which, as I told you at the beginning, is leading to these large energy consumption figures. In biology, every synapse stores its state. So memory is completely distributed. There is no memory block far away. Every single computing node has its own local memory, which is accessed in an asynchronous way. And also the type of memory elements, whether they're in the synapses, in the properties of the neuron, in the length of the wire, they have different time constants, different dynamics. So there is multiple memory structures with multiple time scales and then multiple operations. So the memory and the computation are co-localized. So if we want to really understand how to exploit the properties of a brain to do brain-like computation, we have to really take this seriously. We have to use parallel arrays of processing elements. If we want, for example, a network with 1,000 neurons, we really have to instantiate 1,000 copies of the same circuit. Completely different from doing time multiplexing, where you have one big processor, or maybe 64th or 128 processors that simulate in time with time multiplexing millions of neurons. If you want millions of neurons and follow and really take advantage of the properties of the brain and the computational properties, you need to have 1 million instantiations of the same circuit. So this is leading to the drawback that you need a lot of area. You need space to do this, but the advantage is that you have co-localization of memory and computation, which gets rid of the von Neumann bottleneck, which then improves by a factor of 10, 100, 1,000, or even 1,000,000 the energy consumption factors of these types of devices. The other approach, if we go all the way back to the Carver-Mead approach of the late 80s, early 90s, is to use both analog and digital, in the best way that you can, and wherever possible to use the physics of the devices that you're using. So in our cases, we're using VLSI technology, CMOS, so the physics of transistors. But if we also embrace this new emerging memory technology domain, we should also try to embrace the physics of the memoristic devices and use those to do computation. We should exploit those physics to our advantage. It's difficult, it's very challenging, it's probably going to take more years of research, but it's the way to really get this 100 or 1,000 or 1,000,000 reduction in power consumption and in still keeping high performance. So this is the first of the two things I told you I would like you to remember, that it's really important to exploit physical space at the cost of using a lot of area. That's really, there's no way around that. And brains even do that by folding these sheets of cortical structures across each other, because also the brain has to package all of this area usage of the wetware into a small volume. The other point is the one of time. So we should let time represent itself. As you know, in computer simulations, time is completely decoupled. Simulation time is completely decoupled from physical time. You could be simulating weather prediction of what's going to happen in the next week in a few microseconds, or it might take you hours and hours or nights and days to simulate complex molecular dynamics that in real time take some microseconds. In these neuromorphic approach, if you let time represent itself, you are stuck in the sense that the evolution, the dynamics of your nonlinear dynamical system, your electronic system, evolves in real time. So this means that if you're processing slow signals, your system is going to be very slow. You cannot run many iterations of the same process trying out different parameters. So there is a drawback. The advantage is that by doing this, you are inherently synchronized to the dynamics of the real world events. And because you have this one-to-one match, you have these matched filters like you would do in signal processing, you save a huge amount of power in not having to store the signals, not having to transfer them across. You can actually process them as they are produced. Think of electrodes in your brain, EMGs, IMU outputs. If you process them as they are produced without having to store them, you save all that energy that you need to store it and to transfer it back and forth. So you can process sensory signals efficiently. And this is extremely important in cases in which we want to process sensory signals. We have access to signals that actually are needed or need to be processed. So these are the two main points: exploit time and exploit space, and let time represent itself. And now, just to give you an idea of the circuits that can actually do this, I just have two relatively simple circuits to show you for these types of neuromorphic chips, the chips that use these principles. One circuit is a silicon neuron. So this is a mixed signal analog digital circuit that has current mode circuits that receive inputs, integrate them over capacitors, and then produce digital outputs whenever the input crosses some threshold. And all of these circuits here, these are analog circuits. They operate basically with nanoamp or picoamp currents, and they have millivolt changes. So in the end, you have nanowatt to microwatt power consumption for each neuron. Time is representing itself. So if you have a small current, it will take a long time for the capacitor to integrate this current. It will take a long time for the neuron to produce an output in response to the small input. And we're talking about here tens of milliseconds because we have picofarads and picoamps. And if you take into account a thermal voltage, which is 25 millivolts at room temperature, if you subtract the pico with the pico, you stay with 25 millisecond time constants. And again, these are very slow time constants. It's very difficult to slow down silicon, but it's really important to be able to achieve them if we want to match them to the time constants, for example, of speech, where each phoneme is coming out of my mouth every 50 milliseconds or so. So that's the same range of time constants that is needed for biologically realistic signals, whether it's speech or ECG or EMG or motion or classifying running versus jogging. More or less the time constants are in the orders of milliseconds. And now if you look at the output of this neuron, and if you look at the x-axis here, you see we have milliseconds on the x-axis. So we did manage to slow down silicon using relatively small transistors and relatively small capacitors to be able to match the time constants of the signals that we want to process for doing AI, for example, on wearable devices. And as I told you, the output currents are of the order of nanoamps. What's also important to realize is that this is driven by the input. There is no active component. There are no op-amps that are always on, always burning power. If there is current coming in, we charge up the capacitor and we use the capacitor to do the computation. If there is no signal, if you're not jogging, if you're not moving, or if you're not speaking, then this is completely switched off. It's only dark current, which in fully depleted silicon on insulator FDSOI technology can be reduced to a very small number. And in fact, this work is a 22 nanometer process with FDSOI technology. And we show that compared to the most recent literature, it's one of the smallest, or it's the one that has the smallest power consumption. So it's the most efficient in terms of energy. The paper is by Ariana Rubino. It was just recently proposed a few months ago in TCAS. So neurons receive currents and then they produce output voltages. They are actually output digital spikes. How do we interface one neuron to the other? In order to have a spike going into another neuron, we need a synapse that converts the voltage spike into a current. And these synapses are also very similar. They're analog circuits. It's actually even simpler than the neuron. And this is a simple one. For example, it's receiving a digital pulse here. It's producing a current, which is being integrated by a capacitor, and then it's producing an output current, which will then go into the neuron. So if you have a couple of these, if you put two of these together, you can create alpha functions, which are actually the functions that real biological synapses produce. And in fact, if you see here on the bottom, there is an output measured from a real synapse, and on the top is the output simulated circuit simulations of a silicon synapse. And if you look at the time scales, milliseconds, nanoamps, you see that we are really reproducing the biophysics of real biological synapses. And this is just one. And if we want to have many inputs, of course, this would take up area, as I said, but we can simplify things. For example, let's assume that all synapses have the same dynamics. If they have the same dynamics, this is essentially a linear filter, and we can use superposition principle. So we can put many synaptic inputs, which maybe have different weights. So we can have a weighted sum, which then, so this would be a spatial integration. We sum all of the weighted currents, and then we send them into a temporal integrator, which needs to be only one. We don't need to have one per synapse. We could just have one at the very end. So you could have very compact elements that receive inputs. They have their own weight. Then you have, through Kirchhoff current law, you have the spatial summation, which goes into a temporal integration block, which because of the capacitor is relatively big, which then goes into the neuron. And this is how we create our spiky neural network architecture. If you look at our chips, they all look the same. They all have this basically synaptic matrix array, which is a big memory. Then they have some temporal integration filters, current mode filters, and then some current mode spiking neuron circuits. They receive digital spikes in input and digital spikes in output. So we can use the best of both worlds. We can use all of the digital communication infrastructure that we have for the input and the output, and then we use analog computation, really subthreshold nanoamps, millivolts, for doing all of the sort of the computation inside, all of the dynamics. And this can be, now we're using transistors, but we are collaborating with colleagues that can replace these transistors with memristors. So really you can have a very dense arrays here with memristive devices that can receive inputs. The memristors have non-volatile memory properties, so they can actually store the weight without having to use the von Neumann bottleneck, and you can do the computation at the same time. So it's really co-localization of memory and computation. Now there's this analog digital divide. So should we stay all analog? Should we use some analog, some digital? Where should we put the threshold of switching to digital? In most cases, in standard approaches, as soon as you have the sensory input, you convert it to digital, and then you use all of your digital logic. Now that we are starting to see the emergence of these memristive crossbars, there is usually what happens is there are signals being sent into the crossbar. These are digital signals that are converted into currents and voltages. They come into the crossbar that does this huge weight vector matrix multiplication. Then the output currents are then converted back from analog to digital, and you have your analog weight matrix multiplier with memristors, but you have digital input and output. If you stay analog all the way, you can avoid using these large DAC and ADC overhead circuits, which actually also burn power. So you have a very compact memristive device, memristor crossbar, but then you have a huge DAC on one side and a huge ADC on the other. That's why staying analog also for the input and the output to this synaptic matrix is advantageous. And then that allows you to reduce power consumption. And if we have analog circuits at the input, we can actually control the properties of these memristive devices in a better way. We can change the height of the pulses, we can change the width of the pulses, the shape of the pulses. And if you look at the literature, by doing that, you can actually do a lot of interesting computations. You can use the nonlinearities of your devices. You can use them as stochastic elements. You could do stochastic gradient descent, for example, by using intrinsic stochasticity without having to use random number generators. You could even use them as non-volatile elements that forget. In spiking neural networks, and actually also in non-spiking neural networks, there is a long tradition of doing reinforcement learning algorithms that need long-lasting eligibility traces. And if you use one of these devices as something that forgets very, very slowly, for example, over minutes or hours, you can use that as a source of an eligibility trace. And this has actually been proposed at the latest discuss just a few weeks ago by INDIVERI, using the properties of PCM to create traces that last for minutes, so biologically behavioral timescales. So again, by staying analog, you can really try to exploit a lot of the properties of these devices, and there is the advantage. And then I told you the circuits that I showed you actually use sub-threshold weak inversion transistors, which are known to be noisy. So there's some criticism of staying analog. You know, these circuits are really noisy. The memristors are noisy, the circuits are noisy. How can we do robust computation using this unrobust, unreliable computing substrate? Well, first of all, there is an existence proof. Our brain is unreliable. Our neurons are noisy. They're completely inhomogeneous. But in practice, you know, if we really want to get something to work, how can we do that? And so here I would just like to show you some suggestions for using these analog circuits and still being able to do robust computation. So here we are actually, this again is data from a few weeks ago from my student who is showing that these circuits are indeed noisy. Basically in this core of 256 neurons, we are just injecting exactly the same input current to all of these neurons, the circuits that I showed you before. They do integrate nicely and they reach a threshold, they spike, but the time at which they spike really depends on the properties of the transistors. And because there is mismatch, there is a distribution of time to first spike, which you can see here. In general, whenever we design these circuits, without trying to minimize the mismatch, it's around, the coefficient of variation is around 20%. So we have to live with this 20% variability. So how does nature do it? How can we do robust computation using this unreliable substrate? The easiest answer is actually to just say, let's average. Let's just do average over space, over a population of neurons, and average over time. If these neurons are firing and they keep on firing, for example, at 50 hertz for the same rate, if we just integrate over a few seconds, then we get a reliable number that tells us the average firing rate. So averaging over time and averaging over space actually gives us a way to overcome the problems of the noise. And this is what we've been doing in the last couple of weeks, actually, what Dmitry Zentrikov has been doing. We want to quantify how much can we gain by averaging. And here you see a plot that we did by averaging over 2 neurons, over 4 neurons, 8 neurons, and then integrating over 20 milliseconds, 50 milliseconds, 100 milliseconds, and so on. And we plotted how the coefficient of variation changes. The coefficient of variation is basically the standard deviation divided by the mean. As I told you, when we don't try to minimize it, it's around 20%. In this case, already with 2 neurons, we get about 12%. If we integrate over a small amount of time and over 8 neurons or 16 neurons, we get 6%. Once we know the coefficient of variation, we can actually convert that to the equivalent number of bits. And this is the scale, the color scale here. So there's this nice sweet spot that tells you that if you integrate over 20 milliseconds and use 16 neurons, you can actually get about 8-bit resolution. So 8-bit, if you're trying to do an ANN accelerator and you have fixed point precision, 8-bit actually is quite good. And this is basically just saying all you need to do is you take 16 of these neurons, and if you average over space and then wait 20 milliseconds, you can actually get 8-bit resolution. In some cases, you might need less. And maybe you want to have a fast reaction time where you have a very coarse estimate with maybe 2-bit resolution. And then as you're waiting, you can improve your estimate. So this is also something that can change at runtime dynamically. And this is something that can be done just by using populations of spiking neurons. So this is trying to convince you that, going analog all the way has not only it has advantages, but you can also cope with the disadvantages of this inhomogeneous substrate. And then there's the problem of spikes. There is, you probably know very well, there is this big debate, why do spikes at all? Why not just artificial neural networks? And there are these two camps. One of the reasons to do spikes and one of the reasons the brain does it is because you can then transmit reliably signals across long distances It's just a way to communicate signals across long distances in a very power efficient and bandwidth efficient method. If you don't need to transmit signals long distances, like in the retina where all the photoreceptors are densely packed, then you don't need to spike. But if you do have systems that have, for example, chips distributed across joints of a robot or in a faraway sensor, then using spikes is the best approach to do just from engineering standpoint, in case you want to minimize power and bandwidth for communication, just for the communication part. But also I'd like to point out some false myths. These camps that argue why spikes at all always tell you neural responses are slow. If you have to integrate over long time periods, you lose all the advantage of the low latency. This is true if you think of a single neuron. But again, once we resort to using populations to have robust computation, this is false. This is a wrong statement. This has actually been demonstrated from pure neuroscience experiments by looking at real neurons. Real neurons are also very slow. If you just have a small input to a neuron, it takes 20 to 50 milliseconds for the neuron to spike. So it's extremely slow. But if you have a population of neurons, and they're all sort of uncoupled and independent, and you have the same input, a very small input to the full population, and you look at the average output of the population, you can receive response times that are even 50 times faster than the single neuron response time. So you can really boost the response time of the population. This was proved by Tatiana Tomachenko in 2011 from real neurons, and we can prove it just by using silicon neurons instead of biological neurons and just doing the same exact experiment. So this is one of the criticisms that, if you have single neurons, I agree, you just waste a lot of time, you have to integrate. But once you resort to populations to do robust computation, you get the advantage of having also very fast reaction times. The other criticism is if you want to have, high precision encoding, you need to have high rates. For the same reason, if you need to integrate over short times, but you want to have high precision, you need to have high rates. Again, this is true if you have uncoupled numbers of neurons in a population, but there's been, again, from theoretical neuroscience, a demonstration that this is wrong. You can actually train a population of neurons to encode signals with very high accuracy using a very small amount of spikes. So sparse activity over space and over time. And that results into very low power consumption. So if you follow the theory of Sophie Deneve, Christian Machens, and all the theoretical neuroscientists that are proposing these learning algorithms, you can actually create a network that before learning requires a lot of spikes to encode a signal with low accuracy. And through this learning process, you can actually encode with very high accuracy using very low power, very small number of spikes, any arbitrary signal. And we actually, again, at ISCAS, some students of the Institute actually proposed learning circuits that can be implemented on chip with on-chip learning to actually implement these models of Christian Machens and Sophie Deneve. So both in biology, in theory, and in hardware, we can actually have high accuracy encoding with very small number of spikes. Finally, another criticism that is often said is that if you have a deep network and you want to propagate precise signals across layers, you need these neurons to be accurate. So same type of arguments, but again, now in the case of deep networks, if you have many populations, many layers of populations of neurons. Also, this statement is actually wrong. It was proven wrong by Van Rossum already in 2002. Not only the statement is wrong, actually, Van Rossum was showing that if you have spiking neurons and you want to propagate signals across multiple layers, you need these neurons to be inhomogeneous. You need them to be noisy. Only this way you can actually propagate signals across in a reliable way. And he actually shows it here. If you have some input signals on the bottom and you see what is the output of the first layer, the second, the third, and the fourth, if they're all identical, if you have high precision, bit precise neurons, you only transmit signals when they are above some threshold. On the other hand, if you have inhomogeneous noisy neurons and some respond to low inputs, some respond to high inputs, then by propagating these signals across the multiple layers and taking the average activity, like I showed you in the previous slides, you can actually recover from, even in the last layer, the information that was in the first layer, even very weak signals. So again, neuroscience is showing us that if you have populations of spiking neurons, they are fast, they don't need to be slow, they can be very accurate, without using many spikes. And you can have deep layers, deep networks that can actually transmit this information across multiple layers. And in fact, you need them to be noisy. You need them to be inhomogeneous. Otherwise, these spiking neurons would not work. So this is showing you that, once we embrace this idea of going away from von Neumann, having space and time represent itself, if we have these dynamical systems with these noisy circuits, we can actually get inspiration from biology to actually create architectures that can do computation. And in a recent paper by Elisabetta Chicca and I in Applied Physics Letters 2020, we actually came up with a recipe that argues on how to do these neuromorphic chips, combining the best of all worlds, of analog subthreshold circuits, of fast digital asynchronous communication circuits, and the nice properties of memristive devices, also mixing them with SRAM and TCAM. So the idea is really to mix the different populations of neurons and synapses together to exploit the space, to add capacitors locally to have in-memory computing, to use whenever we can the distributed memory elements, whatever elements we need, capacitors, SRAM, memristors, and then of course to use the best of both worlds, whether it's analog or digital, to just embrace the properties of both analog and digital together. And finally, the trick to have robust computation is also to use negative feedback and adaptation and learning, the same trick that biology uses. So learning is actually a very important ingredient of this recipe for creating these types of chips. And this is an example of a chip that has many synapses. So you see it's a big 2D array of like it's an intelligent memory chip. It's a 2D array of synaptic elements, which are essentially memory elements. And on the side, there are these neurons that actually do the temporal integration and then produce spikes if the dot product of the inputs with the weights is above some threshold. Now, just to give you an idea, this is not all abstract. We've been designing these chips. We've been fabricating them. We are designing them in 22 nanometer, but the latest one we got was from an older process, a 180 nanometer process. It's called Dynamic Neuromorphic Asynchronous Processor, or DYNAP. And this generation is called Dynams. And the latest chip, we can actually create a PCB, put it on a FPGA so that we can do prototyping with it, connect it to a computer and run some algorithms. It's stackable. So each chip has 1,000 neurons. If we need more than 1,000 neurons, we can stack two boards together that host 2 chips. If we need more, we can stack 3, 4, 5, up to 7. So we could have networks up to 7,000 neurons. As I said, the price to pay is area. So in these chips, we don't have 1,000,000 neurons. We only have a few hundreds. And so it's very difficult to do applications that require very large numbers of neurons. But there are still lots of applications, especially in edge computing, that, for example, for auditory processing, that can be done with a few hundred or maybe a few thousand neurons. So these types of chips could be extremely useful for those applications. In fact, just to give you an idea of the type of applications that we had, at the university, we have been exploring. Many are linked to biosignal processing. So we've been studying neural activity of zebrafinch birds from our colleagues that are working with zebrafinch to study songbird learning. We've been working with colleagues that try to build bidirectional brain-machine interfaces with mice and then extend the sensory property abilities of a mouse with the chip that can sense something in addition to the other senses that the brain has. We've been doing it with cultures of neurons. We've been doing closed couple loop between silicon neurons and real neurons and sort of having a dialogue between the two populations of neurons. We've been studying ECG, EMG. I'd like to just highlight one of these types of biosignal processing applications on high frequency oscillation detection, which is going to be the next slide. But before I go on to the next slide, I also would like to say it's not only biosignal. As I said, we can do it for auditory processing. And one nice application that is going to be presented at the next AICAS conference a few weeks from now is on industrial monitoring of vibrations. So it can also be applied to monitoring vibrations, for example, in gearboxes. So this high frequency oscillation is a nice application. And I only show you because it just came out in Nature Communications last week. So it's very, very recent. What is this high frequency oscillation? Basically, these are, if you take recordings, intracortical EEG recordings from human brains, you can find some particular oscillations in the 80 to 250 hertz frequency band, or in the 250 to 500 hertz frequency bands. And these types of ripples are called high frequency oscillations. And these high frequency oscillations are characteristic of those areas of the brain that can give rise to epileptic seizures. So it has a really important clinical relevance for those patients in which it's not possible to cure epileptic seizures with drugs. The only way to do that is to really go there, take out the piece of the brain that is causing these seizures. And to find out which one is the part of the brain that is causing these seizures, one strategy is the one of finding where is the area of the brain that gives rise to these HFO signals. This typically now is done offline. So the subject goes into the operating room, you put this intracortical IEG device on it, you take data, you record all the data, you put it on MATLAB. The researcher goes off, uses MATLAB on a desktop, finds which one is the region that is, the one that is producing the highest number of HFO, tells the surgeon, and then the surgeon goes and resects that region. Even now, using GPUs, the most state-of-the-art deep networks, the accuracy is 60%. So in 60% of the cases, the patient is epileptic seizure-free. But in 40% of the cases, this actually doesn't work all the way. So even with offline approaches, this is still problematic, and it's an important problem to solve. So we actually propose to use the chip that you saw before to actually solve this online, directly in the operating room, like a Geiger counter. You could have a chip that is basically telling you which of the area here is producing the highest number of HFOs. And the surgeon can then, through his own judgment, decide which area to resect. And what we have basically is the chip that has an input low noise amplifier, a bunch of filters to get these ranges of frequencies from 80 to 250 or 250 to 500, and then the spiking neural network with the circuits that I showed you, those spiking neurons and those synapses. And what we did is we actually, we take the signals that are measured from the amplifier, we filter them, we convert those into spikes. So whenever there is a high changing amplitude, it's a positive spike. When it's a decreasing in amplitude, it's a negative spike. We send that in a 2-layer network, a very, very simple sort of extreme learning machine type of network, or you could call it random forest type of network. And without having to do any backpropagation, without having to do any training, essentially basically logistic regression, the basic tools of AI, we then could find out the sets of weights and time constants that are well matched to the signals. And then we actually created the network that, given this input, after converting the input, produces some spikes, some neurons. It's a network with 256 neurons. Some of these neurons detect the HFO, and just a few milliseconds after the presence of the HFO, they spike, and they tell the surgeon, this is the channel that is, this area of the brain is the one that has some HFOs and the others don't. So by looking at which neurons fire more, we can detect which channels of the IEEG device are having more HFOs. And the accuracy with the data set, this has not been done in the operating room yet, this is just with offline data for now, is even better than the state-of-the-art, than the best of the state-of-the-art that we could find in the literature. It's still not 100%, but at least we are more than the state-of-the-art that is being done offline. Again, this just came out a week ago. It's in Nature Communications. If you're interested, you can just click on this link and you will find the full description of the paper. I should just quickly summarize now because we're coming to the end. So I hope I convinced you that this is really an interesting area to investigate from research, but maybe also from applications. But I also would like to point out that these types of approaches are not the solution to all the problems that the tinyML community has. So when should we look at these as, potentially useful types of technologies? It's whenever we need low latency and very, very low power. If we are at the extreme edge and we cannot afford to connect to the cloud and we want to do some low, pre-processing, then this is a technology that is worthwhile investigating. It's good for small scale networks. It's not good for vision because these chips require lots of area to put some neurons on it. but it's very good for real-time sensory processing. If you have spikes, it doesn't matter whether they come from auditory sensors, from IMU sensors, from temperature sensor. You can do sensory fusion once you convert to the same representation. And so it's really useful. It's really interesting to use these applications for multi-sensory classification with low latency decision-making. They are not meant to do matrix multiplications with high accuracy. These are not number crunching devices. I would never use them to control an airbag, for example, in a car. So you really need to be careful when to use and when not to use these types of chips and technologies. And really the best approach is probably to combine them, to complement the two approaches. For example, if you think of using the STM32 that we saw just in the previous presentation, to process the data coming out of these chips and using these chips as a low power watchdog, that probably would be the best combination of approaches, to have low power sort of intelligent sensing and then some higher cognitive processing done by the STM32 chip afterwards. So this is finally the last slide. Everyone in this community knows big data needs a hardware revolution. We are all here working on the same goal. Even Nature recognized it in 2018, and we're actually in a very good position because even though software companies are making headlines, we doing the hardware are actually the ones that have higher potential. So there is this problem of conventional AI that is burning too much power in an unsustainable way. New emerging memory technologies require analog processing and can best exploit the properties of analog circuits. Meanwhile, neuroscience in the last 10 years had made tremendous progress that is showing us how to use unreliable computing elements to do robust and reliable computation with low latency and with low power. So this is really the perfect time to try to embrace this approach and see really, as I said, if we can use it to complement the standard ANN approach. And just to give you an idea, when I tell you it's microwatts versus the hundreds of watts, it's really as if you were comparing a Swallow with a 737 jet engine. There's a really huge difference in power consumption if you look at the type of applications that can be solved with these neuromorphic sensors and processors versus the conventional approaches. So with this, I would really like to thank, first of all, my students that have really contributed with all the results that I presented, and the postdocs, really talented postdocs that are also co-supervising the students. The funding agencies, both Europe and in Switzerland, national. SynSense is actually a startup that is actually producing devices and products following this approach that is also contributing and supporting the research at the Institute. So this is a really promising new AI startup that hopefully will be successful following this approach. And then I would like to thank you for your attention, and I'm open to questions.
Thank you very much, Giacomo, for the very nice tutorial. There are quite a few questions, but there's not a lot of time. I'll have to pick one of them. It's maybe a bit more of a meta question, but one of the questions was, do you think it's limited, or are we limited by our limited understanding of how the brain works in making all of this work? Or
yes, that's basically the biggest limitation. So the Carver Mead already in the 90s was saying, we can put on a chip a huge amount of devices, even more than what's present in the brain of a bee or in the brain of even a small animal. The problem is we don't know what to do with them. I can give you a chip that has 1 million neurons. We have them from True North, from Spinnaker. The problem is really more fundamental in terms of the neuroscience. How can we understand how to exploit this nonlinear dynamical physical system to carry out computation? And there is a formalism from McCulloch and Pitts, that isomorphism with Boolean logic. But really, if we want to introduce the time element, you start to get into these nonlinear dynamics, and it's really complicated, and it requires really not only neuroscience but theory of computation, physics, mathematics. It's really something that requires an interdisciplinary approach to solve these problems. And I believe the general AI, I think, is still far away, but within my lifetime, I think that there is this possibility that we will understand how to solve very basic sensory processing problems. For example, we already see that speech recognition is becoming solvable. It is narrow, but I think that in the future, by combining neuroscience, mathematics, physics, we will be able to create devices that can be as intelligent as say a dog or a small animal in terms of recognizing different keywords, commands, intonation of a command, and so on. But it requires still research from multiple disciplines, not only electronics and material science.
Lots of work left for all of us then. That's good. Thank you very much again for this very nice tutorial.
I would like to acknowledge again our sponsors. The sponsors are the ones that actually made having a free registration for everybody possible, starting by Newton.ai, who is innovating into the automated tinyML domain, who's also our premier sponsor. Next, we have the executive sponsors. We have ARM, which, as you know, builds from both the software and the hardware foundations for tinyML. We have Edge Impulse, who is advocating strongly, as you all know, for tinyML available to all of the developers. And of course, Qualcomm, who is working as, among other perception, reasoning, and action, and edge and cloud devices in various sectors, such as the Internet of Things, automotive, and mobile applications. And Sentient, who is moving artificial intelligence from the cloud to the edge, which, as you have seen today, it's quite now the trend nowadays. Next, we have our platinum sponsors, Infineon, part of your life, part of tomorrow. We have seen a few of their projects that they work today. We have Reality AI, who is working also in pre-built edge AI sensing modules and tools. Next, we have our gold sponsors. Latent AI is the first one who works on adaptive AI for the intelligent edge. Then we have SenseML, which works on building smart IoT sensor devices from various data. And last but not least, our silver sponsors, EMSA from Israel, Greenwaves, HOTC, Magimop, Quixo, Seed, Studio, and of course, ST Microelectronics. I would like to thank everybody that stuck around until now, and I hope to see everybody tomorrow at 4 o'clock Central European Time